All right, good afternoon, everyone. My name is Shritika Thapa. I'm one of the faculties here at Yale, and welcome to our sleep seminar. Just few announcements before I introduce our today's speaker. Please take a moment to ensure that you're muted. In order to receive the CME credit for attendance, please see the chat room for instructions. And if you have any questions or comments during the presentation, please use the chat room, or you can unmute yourself at the end and I will moderate the session. Recorded versions will be available on YouTube after a few weeks of presentation. And now I have the extreme pleasure of introducing Dr. Ioachimescu. Dr. Ioachimescu received his medical degree from Carol Davila University of Medicine and Pharmacy in Romania and his residency fellowship training at MNASTA National Institute of Pulmonology in Romania. He then completed his internal medicine here, residency from Danbury Hospital, Connecticut, and his pulmonary critical care and sleep medicine fellowship from Cleveland Clinic, Ohio. He's currently a professor of medicine at Medical College of Wisconsin, Milwaukee, where he is also the vice chair for clinical research and data analytics and the director of clinical trials office of CTSI, Clinical and Translational Science Institute of Southeast Wisconsin. He's also an associate director of Clinical and Translational Research Center, CTSI, and he has a secondary appointment as adjunct professor of medicine in the Division of Pulmonary Allergy Critical Care and Sleep Medicine in Emory University. His research is primarily focused on data science and artificial intelligence in respiratory and sleep physiology, along with clinical, translational, and health services research. He has lectured in courses nationally and internationally. He has also received many awards and is the recipient of several grants and has authored over 100 publications. It was a long CV that Dr. Ioachimescu had. I cannot do justice in this few minutes. And he has also held leadership position in many national societies and has strong interest in organizational and healthcare leadership and education, and has served on the editorial board on several committees. Thank you so much for being with us. It's our honor, Dr. Tavi. And without further delay, I would like to hand it over to you to share your expertise on a very upcoming topic, AI in sleep.
Thank you, Dr. Thapa. I really appreciate the work of going through that introduction. I appreciate it. I know my CV is pretty long, unfortunately. Let me see if I can put this in full screen. Can you see the full screen, non-presenter mode?
Yep, we can see it.
Perfect. So good afternoon, everybody. As you've heard, I'm Octavian Ioachimescu. I'm in Milwaukee, Wisconsin. What you see in the background is a recent picture I took in one of the parks at sunset. You already have received this. This is my disclosure and accreditation form. I don't have any actual conflicts with today's talk. And in fact, while you're doing the presentation, Dr. Thapa, I was thinking that probably you should have used ChatGPT to do a short presentation. Sometimes it's better than what we can do by looking at the large CV. And as you've heard, I have trained in internal medicine at Danbury Hospital. I would consider that my biggest disclosure today. At that time, Danbury Hospital was pretty strongly affiliated with Yale, and we would have elective rotations in New Haven or West Haven, VA. And we would have actually weekly attending rounds from attendings coming from Yale to Danbury, or we would go to our monthly pulmonary grand rounds at Yale. So those were fun times. So I will, again, thank you so much for inviting me to discuss today a little bit about use of artificial intelligence in the field of sleep medicine. My minimal learning objectives would be to walk you through a few major milestones in the development of AI, walk you through some main advantages of using AI in the field of sleep medicine, and also touch base a little bit on the main drawbacks or pitfalls of using different AI approaches in the field of sleep medicine. I cannot resist not to start with this slide, which is depicting here a drachma, a silver coin from Crete, which is depicting the talon here. You see the name. This was an ancient mythical automaton that apparently possessed artificial intelligence, and I will explain. So in Greek mythology, Talos or Talon was called automaton because it had this charge of encircling the island of Crete 3 times a day to protect the island from pirates or other invaders. And it was an automatic type of behavior. Interestingly enough, the word automaton, which means apparently from Greek acting of one's own will, was first time used by Homer that described automatic door openings or automatic movements of wheeled tripods that were used in different wars. And since then, it has been more often used than to describe non-electronic moving parts, such as jacks or cuckoos on old animated public striking clocks, for example. So what does artificial intelligence entail? Well, it turns out that artificial intelligence sprung up from various fields, from domains such as theoretical reasoning, knowledge representation, believe it or not, planning. So you think about project management, folks have tried to systematize and find automated ways of doing planning of human activities. Of course, activities related to learning and biologic behaviors that are behind the processes of learning. And then natural language processing was a major field in the early days of artificial intelligence. The studies of perception and how we integrate sensorial inputs with other brain activities and come up with specific perceptions related to our sensorial inputs. And then moving or manipulating objects, again, with the idea of having some automated type of behavior. The AI interconnects even nowadays many fields. So from computer science, data science and analytics, information technology, mathematics, but also social sciences such as psychology, sociology, anthropology, linguistics, ethics, and philosophy. So let me start out with some milestones in the development of AI over time. It really started out with mathematicians and philosophers that started to look into the mechanical reasoning or formal reasoning processes and what were the rules behind these. And then, of course, the major advance that happened in the field of mathematics was when Alan Turing came with the theory of computation, which said really that if you shuffle two symbols as simple as 0 and 1, you can simulate any conceivable act of mathematical deduction. That is the basis of the Church-Turing thesis. And then, of course, with the fast advances that we've seen in the field of neurobiology and information technology, with the advances in our computational capabilities and cybernetics, we started to see how researchers are considering coming up with an electronic brain concept and what that entails. How do we code something like activities of an electronic brain system? In the early 1980s, kind of related to this, folks started to look into developing expert systems, which were forms of AI programs to simulate knowledge and analytical skills from human beings, human experts. And then I think another major breakthrough that happened really in the field of mathematics was the development of artificial neural networks in the late 1980s. I only got exposed to that in the turn of this century, so about 20 plus years after it was developed in the theoretical field of mathematics. But this has been a huge point in development for artificial intelligence. So in the last decade of the previous century, AI began to be used more and more in the fields of logistics, data mining, as we started to become better and better at collecting large amounts of information, data analysis becoming a necessity, and progressively in our medical fields to be used for medical diagnoses. I wanted to highlight the year of 2012, which is only 12 years behind, which was a major year for an intersection of three major things, which is we started to have faster computers with significant advances in our computational capabilities and algorithmic approaches, and be able to use large amounts of data that were accumulated fast. And we started to use machine learning and data-hungry deep learning methods started to dominate accuracy benchmarks. And I'm giving you three examples here from maybe the lay world, but you may have seen over time how Deep Blue defeated Garry Kasparov in chess. He was the reigning world champion in chess, and that was a clear differentiation between computer performance and human performance in chess. And then Jeopardy, and then sorry, and then in the field of Go, also where AlphaGo was able to defeat the number one ranking champion in Go. In 2020, the natural language processing systems evolved, and the first one was called GPT, and then GPT-3 became the largest artificial neural network. And clearly, we started to see where the performance of the machines was matching or surpassing the human performance by most of the benchmarks we had in the field. And then also in 2020, DeepMind's AlphaFold 2 was able to determine the 3D structure of a protein within hours, rather than what we were able to do before with computational capabilities within months. So very, very fast acceleration of pace and computational capabilities. Now, of course, we probably were all surprised when we saw 23 months ago, on November 30th, ChatGPT, OpenAI being launched. And it just took the world by storm. I mean, it was not even a couple of weeks later when high schoolers started to do their homeworks by using ChatGPT, and we decided that we are of a different generation, lagging behind already in users of ChatGPT and so forth. GPT-4 was launched only in March of 2023, so only 4 months later. And Gemini also came the same month with their system. And I could not resist not to list you here the explosion of the different AI systems that came from 2019 all the way to 2024. I know it's hard to read. That wasn't the intent really for you to read all those names, but a lot of OpenAI systems or open large language models that started to become available and really started to compete significantly in the marketplace. So when we talk about artificial intelligence, AI, what is AI? Is it an acronym inebriation? Is it an alphabet inebriation? I would conceptualize it as a larger set that in fact will end up with a machine learning subset, deep learning a subset that is of the machine learning. And then you see artificial neural networks being a major subset of the deep learning. And I listed there a couple of other methods, but the number of methods and mathematical approaches is really very large. I listed there support vector machines and decision trees. But we've seen with the ChatGPT, with the generative AI, which intersects with the large language models and natural language processing, this explosion of capabilities. So we're all now in the era of large language model generative AI. So going back, what is artificial intelligence? Well, it's always contrasting with the human intelligence, natural intelligence, which is displayed by humans and or animals. We possess consciousness and emotionality, while computers, software systems having AI, they have this intelligence, the ability to learn. AI was really founded as an academic discipline in 1955. And since then, there have been multiple waves of optimism and development called hypes that were followed by the so-called AI winters, periods where ethical concerns, societal or social concerns, losing jobs, losing funding at times were interspersed between these hypes and winters. And I remember there was a famous quote where one of the Rockefellers was asked in the 1960s, "Are you concerned about artificial intelligence?" And his answer was, "No, I'm not that concerned about AI, but I'm more concerned about natural stupidity." It turns out that each one of these cycles, maybe we became a little bit desensitized, but I think now it's for real and it's here, and we do see the significant impact at a societal level. And a lot of times the AI research took in very different directions over time. partly because they were different goals, very distinct goals, for such as robotics was, looking into one direction versus machine learning, a more theoretical mathematical approach, or specific tools were very different. And sometimes they were kind of very clear-cut, deep philosophical differences between the approaches. Whereas machine learning algorithms work on the premises that strategies, algorithms, deductions, and inferences that worked well in the past will continue to work in the future. And I gave here kind of a tongue-in-cheek example. We all know wake time follows sleep time, right? Machine learning programs perform tasks without being explicitly programmed to do so. Computers learn from data so they can carry certain tasks. And then if you want to categorize the tasks, they go from simple tasks. And in this instance, it may be easier for the human programmer to describe the specific steps to execute for the machine. While if you're looking at more complex tasks, the AI software may be able to explore the data without any programming, if you want, from the human, or pre-guide how to assess the data. And I would also make this, high-level statement that modern-day machine learning, it's still really looking at two major objectives. One is to classify data based on models which have been developed on the data. And of course, we always want to validate these on other data sets, ideally from outside the initial environment. And then the second one is to make predictions for future outcomes based on these models and the previous data. So I kind of described, in other words, the two major domains or two major categories of machine learning here. One is the supervised approach, in which you have a pre-specified target. You have a specific dependent variable or an outcome that you're trying to predict or model. And I'm listing there some mathematical approaches to that, as opposed to the unsupervised approach for machine learning, in which you don't have necessarily a pre-specified target, dependent variable, or outcome that you're interested in. And again, you may allow the machine to do the kitchen sink approach, in which you ask the machine to try to find patterns in the data and even to come up with specific output that you haven't pre-specified. I mentioned the artificial neural networks, and I think it's important to give you a graphic representation and explanation what that is. Think of the data that goes into input layers, and these can be multiple nodes in the input layers that in the end will end up with an output layer, so a specific variable, a specific outcome, and it doesn't have to be one node. It can be more than one. It could be a full matrix or a full column of nodes. And what you have in between is the so-called hidden layers, the thing that has scared a lot of us in the past, and this is the traditional black box. What's going on in between? These are multiple layers, and if you have more than two, it becomes a deep learning neural network. And all of these are nodes in which you have specific equations, specific mathematical computations for both forward propagation and backward propagation in trying to optimize the model. And these are sometimes hard to understand, and that has been over the years a significant tendency to ask to have explainable AI algorithms, but at the same time, they're also very complex. So even if they are very clear-cut types of equations, sometimes it's very hard to understand what's the contribution of different factors and how do you maybe need to prune it and to use fewer equations and fewer layers. But this is in a nutshell the structure of an artificial neural network. And I think we've made huge strides in the field of research, in which when you publish a paper, the reviewers will ask you, what's the architecture of the neural network you've used? And can you justify what led you to this specific structure, this number of hidden layers, or these specific output layer nodes? I should have mentioned that artificial neural network as a name comes from the preconception that turned out to be pretty wrong, that this is how the brain works. Some computational specialists in the early days in the 80s thought that if we have different neurons and that we connect them through synapses, this is how the brain works. And in fact, that's kind of far away from how the brain works if we really knew it very well, even today, how that is happening. So let me go through some major advantages of using AI in general, and I will narrow down a little bit more for sleep medicine. It really allows us to do fast analyses on big data. And now we started to see fast data. So fast, it means really quickly accumulating and quickly developing, exploding that data, deep data, so multiple layers and multiple levels at which you can analyze or pick up specific characteristics from not necessarily at the surface, and also long data. We're looking at data that is collected over time, and this is a good example for what we use in our healthcare system, longitudinally collected data for real-world data from electronic health records. Of course, we've all seen how artificial intelligence has penetrated the field of consumables, and consumer sleep technologies have exploded over the past 10, 15 years. And artificial intelligence provides us this unique opportunity to incorporate variables that come from different fields, from clinical world, from environment, and from the lab objective measures that we collect. And as I said, they can be in a long sequence, such as long data. Hopefully, and I think the next couple of statements are more teleological than anything, this can help us to better understand how do we divide normal versus impaired sleep, and also how do we cluster different features into phenotypes, observable features, or endotypes that are related to the mechanisms of known or unknown new sleep disorders. And I think this is also teleologically there, aspirational. We would want to see that we optimize our diagnostic approaches in the fields of sleep medicine with both supervised AI protocols and unsupervised AI protocols. So similar to the discussion with the machine learning supervised and unsupervised. And to give here a good example is we always use gold standard polysomnography, right? And we always use our EEG assessment of sleep stages based on relatively random, if you want, or preset criteria that have not been necessarily based in biology or other criteria. And if we want to assess new approaches, we always compare it to the gold standard. And I always make this point that we should aim to have as little concordance between a new phenotype, new endotype, or a new way of diagnosing impaired sleep or a sleep disorder against the gold standard, because we want to find better ways. I like this slide from an IBM developer educational product, in which they describe the features, the characteristics of data as the 5 V's. It's important to see that the velocity of acquisition of data is appropriate. You're dealing with the right volume for computational capabilities, the variety of data. We spoke a little bit about validation, internal and external validation, that you can trust the data that you accumulated, and you're analyzing, and what's the final value of the analysis of that type of data. I like this cartoon in which Watson and Holmes kind of swapped roles, and Watson is telling Holmes, "It's elementary, my dear." What I really like about this cartoon is the fact that Watson is showing us the Bayes theorem on its belly there on the screen. Shifting a little bit gears. From 1950s and 1960s, there's been a huge progressive development of the field of diffusion science and then implementation science. And I really like the seminal work of F. Rogers, not in the medicine. In fact, there were just very few papers in the field of medicine, but he described among the first that adoption of any innovation or any new discovery follows this Gaussian or normal curve, in which you have about 2.5% innovators, about 13.5% early adopters, then go to early majority, late majority. And he clustered together the resistors with the very late adopters or last adopters there in this curve of adoption curve. And if you look cumulatively, the orange curve, that's the diffusion curve of innovation, the sigmoidal shape. A different cycle that has been used in the last few decades has been issued by Gartner. Gartner is a company that does a lot of business consulting, and their theory here is that every innovation follows these 5 different phases. It goes from innovation trigger into a phase of peak of inflated expectations, and what you see on the y-axis is the expectation magnitude. And then invariably, it goes through a trough of disillusionment. And if it survives in that trough of disillusionment, then it goes into the slope of enlightenment and then a plateau of productivity. And they describe very nicely how you go from R&D activities to then first generation products, prototypes, early adopters started to investigate, mass media hype, and then it gets to that peak of inflated expectation where the activity is really accelerated after the first adopters take it to the early majority. And then invariably starts having troubles. You start seeing negative press, you may see flaws, you may see performance issues, sometimes supplier failures and consolidations. And it goes invariably to the trough of disillusionment. And as I said, if it survives, it goes back into the slope of enlightenment where you start seeing refinement of methodologies or reframing and how is the innovation used. And then it gets into the mature phase with the plateau of productivity. And sometimes the product goes actually in time to a very different line or a very different market. And I wanted to contrast these 2 curves by saying that there's really no conflict there. After the early adopters, the product can die or the innovation can die off right away. So it's a huge chasm. And if it survives, as I said, this trough of disillusionment, then it can go back into the development and adoption. So I look every year at different technologies and different innovations and how is Gartner classifying. This is kind of a mixed picture. It's both assessment of the current environment, but also they are trying to model this and see what's the pace of a specific domain going in their curve, on their curve. So for example, you can see here quantum AI early on in the innovation trigger, and their prediction is that it's going to take probably more than 10 years to get all the way to the plateau of productivity. And I'm showing you here with this arrow, the generative AI. Generative AI was only last year the peak of expectation. So it goes pretty fast on that curve. And the question is it going to survive going down this trough of disillusionment and then go back up, or it's going to be replaced completely by something else? Very fast movement on this cycle. I wanted to look also at the data science and machine learning in general and look at different domains. For example, prompt engineering is kind of approaching that peak of inflated expectations. Generative AI is going down. And we start seeing where the deep learning methodologies are actually starting to go back up on the slope of enlightenment. So we probably became a little bit better, and this field has become more mature in how we use it nowadays. Computer vision is already in the plateau of productivity, which is interesting. And you may have seen all those wearable, all those virtual reality or augmented reality or mixed reality devices that have been penetrating the marketplace in different fields, including in medicine. And a similar cycle I wanted to showcase for the use of AI in healthcare and life sciences, where we see that data literacy for healthcare and life sciences is really at the peak of inflated expectations. In other words, we became aware that this is an important field, that we have to redesign our educational offerings for our trainees and our future generations. So we're right there, the peak. It went very fast up the slope there. And you start seeing, I find this very interesting, that we're already in the plateau of productivity in 2 different domains. One is the advanced analytics for practitioners, And we may have all seen our, new analytic platforms in the electronic health records, for example. But it's also the advanced analytics architectures for payers. And we may have all seen prior authorization or denials that are AI-based. And if you're really still not convinced that generative AI revolution is real, you call it just a heat wave or a fluke, I wanted to showcase you also an analysis that was published by Gartner, looked at a few thousand executives that have IT roles in their companies. And they surveyed them over a period of 4 months, 5 months, in fact. And it went from blue in April of 2023 to orange in only 5 months. And you see how they were considering, they were exploring initially, 70%. 5 months later, 15% were exploring, but then they went actually significantly to piloting from there and even to production. So very fast development. People started to pick it up. It's not like blockchain or other technology kind of development that kind of were arrested there. So this slide is to remind me that I have to make the comparison if AI is primed for use in healthcare. And it has been quite clear that there is a huge role in radiology, in dermatology, in ophthalmology. There's no reason why sleep, which is based so much on pattern recognition and analysis of big data, would not be another field that would be embracing or be using AI in the near future heavily. I wanted to show you this quick slide on a massive review on diagnosis and treatment of obstructive sleep apnea, which I stumbled over really by looking for something else. A huge number of experts from all over the world that contributed to different sections of this massive review. I like the fact that they had knowledge gaps and research opportunities as one of the sections. And when you look at AI, machine learning, and deep learning, they were 0 hits. They showcased this in 2022 in their paper. And I really think it illustrates nicely the fact that there is a huge knowledge gap and research opportunity for us to be using AI and machine learning in the knowledge or evidence acquisition in our field in the sleep medicine. So I will show you a few slides in which there are different review articles looking at or inventorying the modalities that have been used for sleep medicine. So one of them is sleep staging. And I understand you've had a talk on use of AI in sleep staging. This is from a paper that was published in 2023. And you see the number of the types of signals that have been used for scoring or creating models that will be fitted against the standard scoring using EEG signals in dark blue, EOG, extraocular movements, and EMG, and then others. So we'll probably showcase you a few other signals that have been used in the last few years. We all know the gold standard for diagnosis of OSA is PSG, polysomnography, and I won't bother you too much with this slide. This is kind of basic for folks that are involved in the field of sleep medicine. It's typically done in the sleep lab. We collect a lot of information, and not all of it is used. So there is a significant redundancy there. We have multiple leads, multiple types of signals from ECG, EMG, EEG, EOG, pulse oximetry, belts for efforts, postures, a microphone for snoring, and so forth. And the traditional way of doing it was to have visual analysis and pattern recognition and scoring by human operators. And then of course, we've all seen that there is a significant quality issue there in terms of analysis, as review fatigue could be a factor. And because of all these factors and how laborious this methodology is, it has become limited and cost prohibitive. And of course, this created the perfect opportunity for computer-based assisted systems and surrogate systems such as home sleep apnea testing to be creating a nation appearing there on the market. busy slide. I won't be reading all the words from it too, but I wanted to kind of structure a little bit the information and how do we organize these domains for analysis. So first of all, we have to see if we are to use machine learning AI methodologies, what types of signals are we going to be using? And we can use the different signals from PSG or photoplethysmography, which has become widespread and used in many systems. EKG, pulse oximetry. We've seen new systems coming with repetitive mandibular movements. So AI just using the contractions of the different muscles. And then we've seen analysis of voice, analysis of snoring, photographs, sensor of the movements of the different parts of the face, and so forth. And then you say, when you want to analyze data, what study have you used to train your model and then to validate your model? And I'll show another slide with an analysis, recent analysis of different studies that have been as the sources of this data. And then we do the processing of the signal, which involves a few phases. One is the pre-processing, and we've all been playing with EEG and EKG gains, and how do you change the amplitude and the sensitivity of acquisition. We've all done filtering with different types of filters for the acquisition, time segmentation, and then sampling, and the frequency of the sampling and accuracy of the sampling. And then we look at decomposition of the specific wavelengths, feature extractions. Then we select the specific feature we want to analyze, and there's always that specific trade-off between accuracy and redundancy. Looking at what you analyze in the training set and then in the testing set and maybe in the external validation set. What device did you take the signal from? And we've seen an explosion of devices with different types of signals. And then mathematically, what did you use in terms of classification system for discrimination between normal and abnormal or a specific stage and others? And used mathematical or statistical methodologies, or used clustering-based methodologies. Have you used maybe an artificial neural network or deep learning methodologies such as convolutional neural networks or recurrent neural networks? I'm just exemplifying two of them here. This is an example of how we go through those phases. So we collect the data, we filter, we pre-process, we segment the data, we do a feature extraction, we focus on a specific feature, let's say EKG. You want to do the QT evaluation, you do the statistical analysis. I'm showcasing you here only one methodology, but you can use many other approaches, not only support vector machine. And then you train and test your model for classification, you optimize it, you check it on a validation set, and you may end up with this type of a binomial classification, apnea or normal. I mentioned that different studies use different protocols, and we have some available data set that we can train and test our models. This is from a paper from 2022, illustrating that some of these studies have been heavily used, such as MESA or PhysioNet apnea database, and others are more individual study groups, like you see there in the 44%. And a more recent paper from PLOS ONE is in fact proposing to create a common sleep data pipeline, combining the different data sets. Of course, this implies that we use the same protocol and the same acquisition methodologies, which is not always true. But I think this is the future, where we start seeing the different data sets being collected either with the same protocols, maybe tagged with the universal protocol, and that will hopefully help us to improve our methodologies. I mentioned the different methodologies that we use to analyze. It can go from mathematical classifier, the traditional statistical analysis or logistic regression, clustering-based approaches, neural network-based approaches, or deep learning-based approaches. Let me stop here. Are there any questions along the way? Did I miss, because I couldn't see the chat, did I miss any questions at this point?
We can do it in the end, Toby, but there is
Do it at the end?
Yeah, let's do it in the end.
Sure. Okay, good. I mentioned some of the signals that have been used for different models. Pulse oximetry is a huge one. I mentioned photoplethysmography. It's a device that is pretty, or technology or methodology widely used nowadays. With pulse oximetry, EKG, and accelerometry, the majority of them get the models developed with pretty high accuracy, I would say. We are all familiar with the table of performance assessment for a test against the diseased or non-diseased. Similarly, we're looking at actual versus predicted, with true positives and true negatives. And I wanted to warn you that they are specific metrics that are used for AI-based or machine learning-based assessments. We are used to the positive predictive value, true positives divided by all the positives. For AI, we use precision, which is really the same without multiplying by 100. So it's a number from 0 to 1. We're used to sensitivity. Recall is the same thing from 0 to 1. And then we compute from these two, from the positive predictive value and sensitivity, if you want, this F1 score, F1 measure, which is the harmonic mean of these two metrics, really. We're probably familiar with the Cohen-Kappa score. You look at the difference between the probability of your observation versus the expected or random chance, and the accuracy, which is pretty much the same as in the traditional assessment of performance of a test. I wanted to showcase you in the next couple of slides another way of assessing visually the performance of the model. So these are the confusion matrices, where you're assessing what is ground truth against your predicted stages, for example, in this case. This is three different approaches. One is support vector machine, the other one is k-nearest neighbors, the other one is a multi-level perceptron, so like an artificial neural network type. And you look at the performance. You would want to see that number on the diagonal as high as possible or as close to 1 as possible, and all the others as far away from 1 or very close to 0. And you may see sometimes, depending on the model or the methodology you employ, that F1 score, for example, it's the highest here in the artificial neural network model. But then when you look at what's happening with N1 and N2 prediction, you see some numbers that clearly show us a deterioration of performance. Similarly, in a more recent paper from Computers in Biology and Medicine, from photoplethysmography devices, if you're dividing between wake and sleep, or 3-stage REM, non-REM wake, or deep light sleep, wake and REM, or the traditional sleep stages, then you may see the performance of the device. And again, we see these numbers on the diagonal. Maybe they're not as high as we would want them to see, but then again, when we look at N1 versus N2, these numbers are not the greatest. And you always have to analyze your performance of the model against the specific ground truth. Although with the caveat that I mentioned earlier, that sometimes the ground truth, it's a very kind of dynamic situation, right? And you don't want to overfit against something that is random or a gold standard has been established by lack of evidence, without any evidence behind. So this is an important article if you want to read more about how the AI technology has penetrated the field of sleep medicine and sleep science. Very nice diagram from their paper where they show us what are the major advances technologically, from smartwatches, PPG-based devices, bed sensors, wireless EEG, radio frequency and radio sensors, and then mobile apps and ultrasound that can be used in a portable fashion. And I mentioned to you earlier, there's always a trade-off between accuracy and user burden, and the polysomnography is really there in the right upper quadrant. And then once we trade off that accuracy going lower with different devices, of course, the user burden goes down, and that's actually one of the drivers of developing these technologies. I looked on the FDA website for the AI or machine learning enabled medical devices for sleep. And the majority of them are filtered under neurology here. So a lot of them in the past couple of years. And then I also wanted specifically for sleep, not only in the neurology field, which devices have been cleared, what methodologies, and you see some of them are under anesthesiology, in fact. So huge explosion. So go back to the biases that we're encountering in the field with AI. One is the physical bias. Are we dealing with physiological or non-physiological artifacts in the way we're collecting those signals? And then computational bias. Are we using the right computational approach? Is this artificial neural network better than a logistic regression model and so forth? And also, is your data set balanced or imbalanced? Are you using the right population or not? And then interpretation bias. To what extent, if you detect a difference of 15% or 25% or 5%, that's something that is significant. Is that going to change our understanding or our knowledge? I played a little bit with OpenAI last week, where I said, create an image of a happy sleep doctor. And I got this image here. And I said, well, I'm not a medical student. And then I said, can I get a more seasoned face of and then actually I played even with the type of stethoscope, because I thought I don't want a nurse's stethoscope. I want a Littmann stethoscope. And then when I asked, I want somebody happier, I got a younger folk again. When I asked, create an image of a concerned sleep doctor, I got again somebody very young, as a non-medical student, more seasoned. And the more concerned I asked, the older it became. So then I said, oh, there's probably some implicit bias. How do we program this, and how do we specifically generate an image based on those specific instructions? So I mentioned the bias as one major problem. The other one is the external validation. Once you publish a deep neural network in silico model, can you validate that in the real world? Can you use that in the real world? And there are regulatory aspects that may prevent you to use it. They are payer-based or insurance-based constraints. But really what I'm saying in the next one is a quote from Nature Medicine in 2021 that says, there is undoubtedly huge potential for machine learning to transform healthcare, but going from code to clinic, C2C, is the very hard part. If you want your ABCDs, I came up with this nice alphabetic gradation, but I can warn you that you're not going to be able to fit it in the alphabet. It goes from artificial neural networks to Bayesian, convolutional, deep neural networks, and you can go to extreme language modeling and so forth. I mentioned this paper. I won't go in detail, but it inventories at the time of 2020 publication, what studies have been published, from what type of technique and technique variations. Was it from EEG, from PSG, from photoplethysmography, and the specific references are listed there. I also mentioned that there is a regulatory environment that is extremely important, and now we have good machine learning practice principles that have been published in association, for example, between U.S. Food and Drug Administration and the Canadian agency. A European Union came with a huge document of regulatory aspects for machine learning and AI. By the time they published, it's already obsolete, so have to be adapted and to keep up with the advances. I won't go too much into detail, but if one wants to implement AI in the field of sleep medicine, you have to be aware that there are some domains of barriers. So one is technological and interpretability, the type of data you use, what's the regulatory environment, can you use that in the actual healthcare practice, human resources related issues, and educational and cultural issues. Now, I'm not advocating necessarily for this talk that we should be all going to read Scientific American, but this statement from 2020 says some types of artificial intelligence could start to hallucinate if they don't get enough sleep or rest, just as humans do. Two things. One is, it's not related to how rested or not rested are the machines. Second, I would not call them hallucinations. I would call them confabulations. These are large language models that kind of backfill areas that don't exist, and sometimes they look pretty false there. But I would also invite you to think about, in our medical decision processes, in diagnosis or in treatment or in our discussions with the patients, how many times a human operator doesn't confabulate? And I will let you answer for yourself, but I find that while this is a significant concern and we have to reduce the rate of hallucinations or confabulations, we should think about the stringency that we employ ourselves as human operators. I have used this slide a couple of years ago, a quote, and this was published in 2020 from Jeff Hinton, who says, deep learning is going to be able to do everything. I think it's challenging. It has become more and more interesting because Jeff Hinton just got Nobel Prize for Physics for the advances made in the field of machine learning and artificial intelligence by using principles from physics into the field. So it kind of strengthened that my inclination or my idea that this may be important. I use these slides a lot when I'm being asked, do you think I'm going to lose my job? Do you think the machines will replace us? And it applies to practitioners, but technologists and other categories. And I think the quote is good, will not replace you, but physicians using AI will soon replace using those not using it. I want you to think about AI in three major categories. One is the assistive AI category, in which this is like computer-aided detection systems or scoring of systems. It doesn't analyze the data, it doesn't make any diagnostic or management decisions, and requires the physician or practitioners to interpret the data. The augmentative AI is the next level, where you start seeing some analysis of the data, but still requires a clinician interpretation. Again, there's no decision for management or for diagnosis. But the autonomous AI, and we're all familiar with the autonomous vehicles concept now, is the one that analyzes the data, starts making recommendations or diagnostic considerations, and it doesn't necessarily require a clinician. Maybe the clinician will become a stopgap before confabulation makes its way into our decisions. But while I did struggle a little bit to give some examples, I ventured to create some there for the autonomous AI. So if you're very biased against AI, you may say autonomous AI is not here yet in the field of sleep medicine or in healthcare, and you may be right. But I think if you think in these terms, you may see how some technologies evolve very fast and how we move away from the early stages of assistive AI all the way to the autonomous AI. I have included a couple of slides, 3 of them, in fact, for a couple of important papers. If you want to go and read more in detail how AI is used in the diagnosis of sleep apnea, for example, a recent review article from JCSM. This is another great one from JCSM where it looks at the performance of different wearables that have been used in sleep medicine. We have 9 wearables cleared by FDA. 7 of them have used AI algorithms, very different. They're proprietary, of course, but a lot of them are actually still based on photoplethysmography or peripheral arterial tonometry. And I've seen this recent meta-analysis that looks at the risk of bias of the different investigations. And, I showed you there, the red and yellow, risk of high or unclear risk for the different domains. I was a little bit surprised by the conclusion, but this is the conclusion. Its current performance is suboptimal for routine clinical use. And I wanted to remind you of Amara laws, that we tend to overestimate the effect of a technology in the short run and to underestimate its effect in the long run. So I will stop here with the reminder that you should be always prepared to embrace an innovation that is of breakthrough. If you're too busy or too preoccupied with your square wheel, you may be missing on the big one, the round wheel. But this is my last slide, and thank you so much for your attention, and we're ready for questions and answers.
Great. Wow. Still digesting it. Thank you so much, Dr. Ioachimescu, for your detailed and very insightful, excellent presentation on this very new and upcoming topic. And also thank you for your suggestion on using ChatGPT for CV summary. With this, we'll open the forum for questions. First question is from Dr. Ian Murphy. Any specific thoughts on open evidence, which is built as a mix of ChatGPT and PubMed?
I have more concerns than suggestions on this one because I'll give you an example. There was this segment on the radio. Somebody asked, should we eat rocks? And ChatGPT, OpenAI, looked for the answer and found 2 editorials that said, this is like eating rocks. But that was used for the machine learning algorithm to conclude that eating rocks is okay.
Wow.
Now, this may be concerning, but the next layer is even more concerning because the fact that somebody did that search on OpenAI is going to strengthen the evidence for the next one who's going to do the same search, which tells me that we have a phenomenon of amplification of non-true data. And how are we going to sort it going forward? It's a matter of huge concern. We've seen the acceleration of publication during the COVID years, right? And how some of the publications have great science behind, some of them not. How do you sort it out? If we start incorporating AI, open AI, large language models, types of evidence, what mechanism we're going to have in place? I'm being told by my colleagues who are specialists in AI and coding that they can actually improve the coding mechanisms so that you start sorting out the eating rocks part that is not being true instead of being amplified, being de-amplified and disappear as a level of evidence. But it's concerning. And we may end up with a complete new PubMed going forward of sorted type of evidence for what we're generating in terms of literature or investigation. Does that answer the question?
Yes, I think that's where human AI is needed. Next question is from Dr. Gara Burgelli. For pre-processing of the data, do you assume that the machine model would need to fit what a human person needs to perform an interpretation, like with gain, sampling, frequency, or since machine learning models are looking at many more data points than human eye can, would that supersede the prior one?
Yeah, it's a loaded question. So I would say unsupervised approach is probably going to be better. Think about, we've been looking on the EEG at the alpha range. You say 8 to 12 or 8 to 13 hertz is alpha. And if you see it in the occipital leads, then you say, okay, this is evidence of wakefulness. But we forget that there is a mu range, mu band that is actually overlapping. It's a smaller one, it's 9 to 13. And it's generated mostly in the frontal areas. So how come we missed on that? How come we didn't look at what is local wakefulness versus sleep in the different area of the brain while we were developing our gold standards for wake versus sleep? So that's an argument to say we have to be open for the machine to pick up patterns and use them in an unsupervised fashion to make us make advances. Because I think if you start quantifying by doing Fourier frequency analysis in the frontal leads versus the occipital leads, you may see differences. You may start separating mu versus alpha, and you might start discovering some interesting things. We're still in a kind of stone age of sleep medicine, and the technology is moving fast. We just need to be able to grab it fast and make those advances fast. Did that answer the question?
I think so. Yeah. Thank you.
Yes, thank you very much. That was great.
In the interest of time, it's 2:59, but we still have a few more questions. So if people have to leave, please feel free. The other question is from Dr. Yagi. It's a fantastic talk, Tavi, with clear implications on our field. One concern about AI we have recently become aware of is the enormous energy demands for processing data queries. Can you speak to this, and is this sustainable?
So yeah, this is it's a significant concern, right? Because the information is exploding in more than exponential fashion or at a high power there. And computational capabilities are one thing, but the second thing is how do we redesign the system in which we're collecting the data with the same protocols, the same pre-processing algorithms, and then we tag it, because I think that's important. We start looking at real world data. If we put all the sleep studies together that we're doing from now until next year, what tagging protocols are we going to use? How we're going to collect and analyze this? And what types of mechanisms we put in place into bringing it back, de-tagging, re-identifying, connecting it to a different database, or not de-identifying, but creating the same tagging protocol. So then you can say, okay, I was really interested in seeing if hyperuricemia is connected to the severity of sleep disorder breathing, and I can establish that very easily from a large data set. Does that capture the question?
I think so. Dr. Yagi was here. Just
Okay.
I have another question by Dr. Andrei Zinchuk. Thank you for a wonderful talk. You shared some very nice examples of using machine learning and AI to assess the sleep, example scoring, staging, etc. There are now appear to be dime a dozen. Do you know of any examples where AI machine learning assisted care compared to the usual care is associated with improved outcomes with symptoms, etc.?
Short answer, no. Longer answer is that I'm glad the question has been asked because we've been looking at the wrong place. If we keep looking at fitting for AHI, we're not going to get anywhere. And we should be looking at hardcore outcome measures. If somebody's developing diabetes, isn't that a better way, more objective way, more important from a health point of view? And I would say absolutely. And if we go back and say, okay, we're going to have to change our standards, the way we assess sleep or the way we assess sleep disorder breathing or insomnia or other condition we want to assess against that specific health outcome, that would be important. I think we have the advantage that we don't have a zillion of sleep disorders yet, and we can do that very well against hardcore outcome measures. But you're absolutely right. This is the most important things. Let's focus on the outcomes.
Thank you. And Clara says, my favorite quote from this talk is I'm more concerned about natural stupidity than artificial intelligence. And I think the last question here is from Shashank Vasipalli. Thank you for the insightful talk. When combining sleep data sets made from various recording devices, how might variations in sensors and sampling rates affect model performance? Could it aid generalization and lead to a breakthrough in performance, or would it introduce too much noise?
Yeah, it's a good question. No data is worse than data, even then data is not perfect. But once you have big data and fast data and deep data and long data, then all of a sudden you can start analyzing and teasing out, right? If you think that peripheral arterial tonometry or pulse arterial tonometry device is better than another one based on the same technology, analyze it, prove it. Look at what makes it different. Is it the sampling frequency? Is it the type of signal it's using? Is it the type of computational cloud-based system that it's using? And we can definitely sort out what's better than other, right? But if you don't have data, if you just start a priori with some assumptions, you may miss the point. But great question.
Thank you. And then last comment from Dr. Francois Roux. Thank you for a wonderful talk.
Thanks,
Again,
Francois.
anyone have any other question or want to unmute themselves to ask Tavi? I don't see anything.
The advantage of a virtual presentation is that I don't get tomatoes thrown at me, right?
Well, we could have flowers thrown at you, I think, with this great Tavi. All right, thank you so much for joining, everyone, and thank you so much for this presentation, Tavi. Really excellent, with this upcoming field. So thank you again for agreeing to talk to us.
Thanks for inviting me, and I'm always glad to see my Yale friends, even on a small screen.
Bye-bye.
Have a good day. Bye-bye.